Hello and welcome to this week's review video. This week I'll be talking about DRAMs. Now DRAMs are a type of volatile memory and it holds a middle place on the memory hierarchy. That means it has a moderate size of storage space while having a moderate access time. Let's talk about the operation of DRAM. The DRAMs holds a one capacitor, and that capacitor is used to store data. If the capacitor is fully charged, it means it stores data 1, and if it charged none, it stores none of the data. So in a typical write operation, a write line wire is turned on and it switches on the MOSFET, and the MOSFET is used as a access point to give the capacitor its charge. So when it's fully charged, the operation just stops, and the write and the read operation is completely the opposite of write operation. Write operation just charges the capacitor, and the read operation just discharges the capacitor. So you can just use it store data. Let's talk about the size of the DRAM. The DRAMs are measured in feature sizes other than the nanometer scales that we are very familiar with. So a typical DRAM sizes are 4 feature by 2 feature size equals 8 features squared. However, there's another way. However, as you guys all familiar with the trend here, the more integration we have, the more data and the more resources we can utilize. So by tilting the DRAM layout, and that is called a open bit line, and using that method we can achieve a size of 6 features squared, 6f squared to be exact. And plus there's another more advancements. This time it's not in the layout, this time it's the whole structure itself, where we knew that transistors are not in the planar device, but rather we used a transistor. We used the cell capacitor as a monolith. So using this method, we could achieve a more higher integration, and this scheme makes the DRAM size smaller, resulting in 4f squared. Thank you for listening. This has been Myung Kim.